All right, so today we're going to start talking about perturbative anomalies in global and local symmetries, and we'll start with the most important example, the chiral anomaly in the chiral invariance. And we'll see that the anomaly is associated with a specific type of one-loop diagram. Then we'll go to the non-abelian case. And finally, we'll go to gauge anomalies, and we'll see what those mean. All right, so first, let me tell you what chiral invariance is. So we know that in general, for a symmetry of this type, where phi goes to phi plus a parameter times the generator of this symmetry times the field, then the Lagrangian can either be invariant or, in general, be the parameter times the total derivative of a current. And then the Noether current is the variation with respect to d phi, d mu phi, times the generator times phi minus this total derivative. And then this Noether current is conserved, meaning d mu j mu a is equal to 0. The specific case that we're interested in is the case of free massless, massless fermions interacting with a gauge field. Specifically, let's go to Euclidean space, and then the Lagrangian would be psi bar gamma mu, covariant derivative d mu, meaning del mu minus IE a mu, times psi. And in Euclidean space, psi bar is psi dagger times gamma 4. When we rotate back to Minkowski space, that would correspond to psi dagger I gamma 0. And the chiral symmetry is a symmetry where where psi of x goes to exponential I alpha times gamma 5 times psi. So in some sense, then gamma 5 is the generator of this symmetry. And then at the infinitesimal level, if alpha is infinitesimal, then the variation of psi is I alpha gamma 5 psi. But then you see that also psi bar varies. Psi bar goes to, since psi bar is psi dagger times gamma 4, and gamma 4 with gamma 5 anti-commute. No, you don't even need to know about anti-commutation. So psi dagger will go into the dagger of this thing, which is psi dagger times e to the I alpha gamma 5 dagger, but gamma 5 dagger is gamma 5, so this is psi bar e I alpha gamma 5. Right, and so the variation of psi bar at the infinitesimal level is also psi bar times I alpha gamma 5. But so that means in particular that the Lagrangian is indeed invariant, because I have psi bar gamma mu d mu, which doesn't matter with respect to just a moment, somebody wants to get in. So I was saying that Lagrangian is psi bar gamma mu del mu, but del mu doesn't matter with respect to matrix indices times psi, and then this varies. This goes to psi bar e to the I. Well, let's say at the infinitesimal level. So the variation is I alpha gamma 5, but gamma 5 anticommutes with gamma mu. So the variation, when I put it on the right hand side of gamma mu, becomes minus I alpha gamma 5 and cancels with the variation coming from psi. So because of this gamma mu, then the kinetic term is invariant. But then if I would add a mass term, that would break the symmetry, because then m psi bar psi would go to m psi bar e to the 2I alpha gamma 5 psi, which is not the same as m psi bar psi. All right, and then the chiral current is, as before, we said we vary with respect to d mu phi. So d mu phi is here, so variation is psi bar gamma mu. And then on the right hand side, we put the generator, which, as we said, was gamma 5 times psi. So the chiral current is psi bar gamma mu gamma 5 psi. And it's conserved, meaning its variation is 0. Because, well, I mean, yeah, just because of the another theorem. Okay, so this was at the classical level. Now at the quantum level, because of the because of general quantum mechanics theorems, we know that what we expect to have is that the vacuum expectation value of this object d mu j mu 5 should be equal to 0, which, if you remember, we call this kind of identity, we call this a word identity, because in principle from it we could derive relations for the variation of for the vacuum expectation value of for Green's functions. So let's remember the derivation that we had for this, just to see what can be changed. So we said that we can just, if we have a global invariance that takes a field phi to phi prime, in the partition function, I could just redefine the integration variable to be phi prime instead of phi. Then nothing changes. So I have this trivial identity. But then if the Jacobian for the transformation from phi to phi prime is 1, that means if the measure is invariant, d phi prime, d phi equal d phi prime. This is the important step. Then we have this. Then we can replace d phi prime with d phi, and then I have integral d phi exponent minus s of phi prime minus e minus s of phi. But if this is infinitesimal, I can take the variation down and say that I have minus integral d phi variation s exponent minus s. However, now we have to be more specific. So let's say the point we're analyzing is a global symmetry, meaning under this global symmetry, variation of s is 0. But then let's consider a local version of this global symmetry, in which the variation of s will not be equal to 0, but will be equal to integral of the derivative of the parameter which now depends on x times this current. By partial integration, assuming epsilon goes to 0 at infinity, I have minus, because of partial integration, integral epsilon times d mu j mu a. And now we substitute this variation into here, into the path integral. And then we see that we have integral of x, epsilon of x, and then path integral with d mu j mu a inside. And since this is for any epsilon, and any epsilon of x, I can peel off this, and I have just that the vacuum expectation value, meaning this partition function with d mu j mu a inserted, is equal to 0. And then we can get other word identities if I insert inside also other fields. It's in the partition function. All right. So by this derivation, we've seen that if the Jacobian for the transformation of the measure is 1, then we obtain this indeed that this vacuum expectation value of d mu j mu a is 0. But reversely, then, in order for this to be non-zero, which we define to mean that we have a quantum anomaly, that the symmetry is anomalous at the quantum level, then that can only appear if there's a non-trivial Jacobian for the measure from the point of view of the path integral. All right. So, but we'll describe the path integral method in the next lecture. But in here, we are interested in the in Feynman diagrams. We're interested then in this in the anomaly in this specific global symmetry called chiral symmetry. In other words, in the chiral anomaly. So we'll see more precisely in the next lecture in this path integral derivation that the anomalies are actually one loop exact, meaning there are no perturbative and no non-perturbative corrections to it. And they, moreover, arise in dimensions in even dimensions, d equal to n, from the one loop diagrams with n plus 1 vertices, where one corresponds to the symmetry current, or more precisely d mu j mu a, and the other n corresponds to the gauge currents in the one loop, coupling to external fields a external. So the coupling to external fields. So what that means is, if we look at in here, so in two dimensions, n equal to 1, so I have one external d mu j mu a, one external gauge field. So the one loop diagram is this. So I have this bubble with the d mu g mu a to the left, and external gauge field to the right. Then in the next anomalous dimension is 4. As I said, we only have anomaly in even dimensions. So in 4 dimensions, which is actually the one that is most relevant for physics, it's a one-loop diagram with 3 vertices, one of which is d mu j mu a, the other being external gauge fields. So that's a triangle. Triangle anomaly, meaning that I have one loop triangle, and then here I have d mu g mu a, and here I have a and a. Well, if you can continue this, so we have a bubble in 2 dimensions, a triangle in 4 dimensions. In 6 dimensions, then it would be a box, meaning there are 4 external lines, vertices, 1 with d mu g mu a and 3 with a. And you can continue further even, then in 8 dimensions it's a pentagon, and 10 dimensions is a hexagon. So now let's do this explicitly. We'll do the calculation explicitly only in 2 dimensions, simply because, well, the calculation is not that long. In 4 dimensions, it's longer, and well, I mean, we could do it. There's no problem, but it's just algebra longer. So I'll just state the results at the end. But in 2 dimensions, we'll do it exactly, and then we'll see we can generalize. All right. So the Euclidean Lagrangian, as we said, is this psi bar gamma mu d mu psi. And then, of course, in principle, this gauge field has a kinetic term. There's some ghost and gauge field, gauge fixing. But this dynamic part for the gauge field, we're not interested in it. We're just interested in this massless fermions. And the gauge field that comes in the covariant derivative is thought of as some external field. So we can forget about this. So we can just say that the kinetic part S0 is psi bar del slash psi. And the entire interaction part is minus IE integral psi bar A slash psi. So the anomaly then is d mu j mu 5 vacuum expectation value, which means path integral d mu g mu 5 with this exponent of E minus S interaction, which is e to the plus IE integral psi bar or A slash psi, and then also E minus S0. And to normalize, we should also divide by the partition function with no insertion. So we do the usual loop expansions, and so we have the free part, and then the interaction part. So I just I just have this vertex, i.e. psi bar a slash psi inserted inside the vev. So I can take the integration over the external field outside, and then here I have the vev of psi bar at psi bar gamma nu psi at y, and d mu g mu 5 at x. Now the zeroth order part, the tree order part, is 0. The reason is because so there's no there's only one x here. So this would be d mu of the current psi bar of x gamma mu gamma 5 psi of x. And so this is a psi integral over path integral over psi of x psi bar of x. And then this would this psi and psi bar, it's at the same point. So when I do the integral, well, if you say I would have something like a propagator from x to x, which is divergent, but also it's what it's interesting for us is the fact that the trace structure. So the trace structure would be proportional to delta alpha beta, and then this would mean that I contract the indices of gamma mu gamma 5, meaning that I have trace of gamma mu gamma 5. But we know that trace of gamma mu gamma 5 is 0. This is one of the generators generators in the completeness relation for gamma matrices. So that means that at one loop, we can, so the anomaly, the vev of d mu g mu 5, is just the one loop part, which is i.e. I can peel off the derivative with respect to s because the integral is over y. And then also the integral over y and the gauge field at y. And then I'm left with what? So I've reordered this in terms of in such a way as to have propagation from x to y. So to have, but the point was to have psi and psi bar next to each other. So I have then, so this gamma nu, this can get outside of the vev. So gamma nu as indices alpha prime, beta prime. But then I have here, let's see. So gamma j mu 5, I called it, I guess, psi bar alpha prime. Psi bar alpha prime, gamma mu no, sorry, psi bar alpha, gamma mu gamma 5 alpha beta, psi beta. So that's j mu 5 of x. And so I separated gamma mu gamma 5 with alpha indices alpha beta. Then I put the psi bar in here and the psi in here. And then I'm left with this other thing, which is a gamma nu with indices that I called it alpha prime, beta prime, and psi bar goes together with the psi in here. So goes like this, and then this psi goes like this. So I have the vev of psi beta of x, psi bar alpha prime of y, and the path integral, the tree path integral, or unperturbed path integral. Then the same thing for psi beta prime of y, psi bar alpha of x. So this is the free propagator, this one, between x and y. This is another free propagator, but from y to x. Yeah, so then contracting the indices, I have this trace of propagator x to y, gamma nu, propagator y to x, gamma nu, gamma phi. And then at y, I have this insertion of the external gauge field, a nu, external at y. So now if I look at the interpretation is really this, that I have, here I have d nu, g nu, j mu 5, because of well, I have d mu here, and then gamma 5 with psi bar. So I have in here I have the current, whereas in the other part, sorry, I was looking at here. Here I have the current, and on the other side I have the external gauge field, external at y. So it's easier to look at in momentum space. So if I go in momentum space from here, then I have a external with momentum minus p, and and then well, I guess so minus p at one end and p at the other end in order to have momentum conservation with the all-in convention. That's why I have minus p. And then from the loop integral, I have this integral over k, the loop momentum, and correspondingly the propagator at with momentum k and the propagator with momentum k plus p. Right. So then this is really this Feynman diagram. So I can pull out this part with the coupling E, the momentum P, and the external field A nu external at minus P, and then the result, the rest I will call T mu nu of P, just an expression that depends on the momentum P. But to calculate this, we'll use dimensional regularization. This is a loop integral, so in principle, it can be divergent. In fact, you will see that there is some divergence. So we need to regularize. So we use dimensional regularization. And as usual, we introduce that dimensional transmutation parameter mu. And this free propagator for the massless fermion is minus I over p slash, or minus I p slash over p squared. So substituting in here these two momenta, we get for t mu of p this this expression. There's this power of mu, which just fixes the dimension. But that's outside, doesn't matter. Then there's this loop integral over a trace, something in the numerator, and then in the denominator, k squared and k plus p squared from the two propagators. But if you look here, the trace structure is, so there's only one trace structure. It's trace gamma. Well, here will be gamma alpha, gamma nu, gamma mu, gamma beta, gamma mu, gamma phi. But I can use the cyclicity of the trace, put gamma mu, gamma phi in front. So gamma mu, gamma phi, gamma alpha, gamma nu, gamma beta. And then I have this integral over k alpha, k plus p beta, over the numerator k squared, k plus p squared. As usual, we do the Feynman parametrization. So I write this product of denominators, k squared, k plus p squared, as one denominator squared. So k squared plus 2 alpha k p plus alpha p squared squared, with integral from 0 to 1 over the alpha. And then I also, as usual, I shift k to k prime, which is k plus alpha p, which eliminates the linear part in the denominator. And now I'm left with k squared plus p squared alpha alpha 1 minus alpha. So when I do this in the numerator, I also have now k prime minus alpha p alpha, k prime plus 1 minus alpha p beta. So now I can divide this into two integrals, one that has indices, so has k prime alpha, k prime beta, and one doesn't, because the indices go on the momentum. So this is minus alpha, 1 minus alpha, p beta. But as we know, well, we did this analysis in lecture 6, and we've seen that, well, by Lagrangian invariance, this is proportional to delta alpha beta, and then we can do the integral, blah blah. We got this result, which was divergent. Was divergent. The reason was we are in 2 dimensions. So here we have integral over, so the integral d2k, kk, so there are 4 k's, and downstairs are also 4 k's. So this is a log divergence. In dimensional regularization, it amounts to 1 over 2 minus d. This corresponds to the log divergence. Whereas this one, this part is not divergent. This is finite because it's integral d2k over k to the 4th, right? So, so this is finite and gives this result. Okay. Yeah. So then we're left with the integral over alpha, which I've put outside, and then some power of momentum here, which is just infinitesimal power, 1 minus d over 2. So D is approximately 2. But then this piece is now divergent. The piece proportional to delta alpha beta is divergent, like 1 over 2 minus D. Whereas this second piece, proportional to P alpha P beta, is finite. So now we remember that in the expression T mu of P, the integral I is multiplied by this trace of gammas. And in 2 dimensions, this trace of gammas multiplied with P alpha P beta is 0. Well, I've written the general form for this integral. So it's a yeah. So you can look at the possible Lorentz structures and figure out that the parts that contract P alpha with P beta, delta alpha beta, are proportional to D minus 2, whereas the resulting ones are with epsilon alpha beta, which gives 0. Anyway, so I don't remember in which lecture we did these traces, but we did them, and in 2 dimensions, this trace symmetrized over alpha beta gives 0. So I can drop this second term. This is finite, and then this trace in 2 dimensions is 0. So I can just drop this. But I cannot drop the first term because the first term was divergent in 1 over 2 minus D. And then I said this trace was equal to 0, but only in D equal to 2. Out in dimensional regularization, this is not 0. Yeah, okay, so I've written here specifically what how we calculate this. So so I write, so we have here oh, sorry, yeah, this is proportional to delta alpha beta. So the first part is proportional to delta alpha beta. So I contract alpha with beta. So then here I have gamma alpha, gamma nu, gamma alpha. So gamma alpha, gamma nu, gamma alpha. I can anti-commute gamma nu with gamma alpha. I get minus gamma nu, gamma alpha squared, plus the anti-commutator, which is 2 gamma nu, 2 alpha nu times gamma alpha. And then gamma alpha squared is D. The dimension D times the identity. And then we get 2 minus D gamma nu. So substituting inside this trace, we get 2 minus D times gamma nu, gamma mu, gamma 5. And this one is proportional to just epsilon mu. It's just minus I epsilon mu. Because of, I mean, gamma 5 here, we're in 2 dimensions. So we call it gamma 5, but what we mean is the product of the gammas, so gamma 1, gamma 2, with a minus I in front. So yeah, so that's why, and then gamma 1, gamma 2 yeah, so gamma nu, gamma mu with gamma 1, gamma 2 is epsilon mu nu. The trace. So yeah, I mean the reason we could use this is that gamma mu, gamma nu is we can rewrite it then as minus I epsilon mu nu gamma 5. Sorry, I gamma epsilon mu nu gamma 5. I times minus I is 1. Epsilon mu nu. Then this is epsilon mu nu gamma 1 gamma 2 plus delta mu nu. So you see, this is what happens. You can go. You can think of what can happen. We can have 1 1, 1 2, 2 1, and 2 2, and you could see that the indices match for this relation. All right, so so then this this trace is this trace contracted with delta alpha beta, like we have in this non-zero term. So I have this delta alpha beta. So this trace gives, in the end, something proportional to 2 minus d. So 2 minus d epsilon mu nu. But I had 1 over 2 minus d divergence from the loop integral. So now I get something finite from the trace. So finally, then, the expression T mu nu of P is, I have this 2 minus d canceling. I have something with epsilon mu nu, this power of mu, so mu to the 2 minus d, then p to the same power 2 minus d. So it's p squared over mu squared over to the power d over 2 minus 1. That's just fix these dimensions. And then some finite integral, I can calculate what that is in 2 dimensions. Since now the divergence canceled, I can just put d equal to 2. So the mu p squared over mu squared becomes 0. And we're left with the integral of alpha. Mas eu tenho que pagar. Vou usar o cartão. Pago e você transfere. Ok. Ok. So yeah, we'll just replace this d equal to 2. Then I get gamma of 1, which is 1, and then in here this power is 0, so I get just 1. So in the end, T mu nu of P is I over 2 pi. This is what we're left with from here. This is 1, and then 4 pi. Well, there's a 2 from here, and we're left I over 2 pi epsilon mu nu. So finally, then the anomaly, which is p mu g mu 5 of p. The vev of p mu g mu 5 of p. The anomaly is this E p mu a nu external of minus p times T mu nu of p, which was I over 2 pi epsilon mu nu. So gives this this relation. And now I have epsilon mu nu with p mu and a nu. And so so that forms the field strength in momentum space. Another way to say it, we go back to momentum to position space. this becomes d mu g mu 5. And in here I have momentum becomes del. So this is del mu a nu minus, and I can anti-symmetrize because this is multiplied with epsilon mu nu, so it's del mu a nu minus del mu a mu over 2. And this is the field strength. And so finally, in the end, what I get is I e over 2 pi times this f tilde external, which is just 1/2 epsilon mu nu times the external f mu nu. Okay, so then finally going back to Minkowski signatures, the anomaly is e over 2 pi times this f tilde external. All right, so you see what we obtained. So the anomaly, the vev of d mu g mu 5, is the coupling divided by some pi's and 2's and so on, but the coupling. And then it's a field strength, which is gauge invariant. But this thing has no indices, so then the field strength is actually should have been multiplied with epsilon mu nu. So this was in some sense expected, right? If you think about it, this is what you expect to obtain. That d mu g mu 5 is the coupling times some gauge invariant combination, which is just the field strength epsilon mu nu, and then some 2's and pi's, which you can fix. So so you can do exactly the same calculation in 4 dimensions, and in 4 dimensions we have a similar calculation. The only thing that we do is we get a triangle anomaly. So you have the same calculation. You also can see that the tree level result is 0 just because it's proportional to one of these traces. That is 0. And then you concentrate only in the one loop result. And in the one loop result, you would get in the one loop result, you would get you would get two gauge external gauge fields times something with 4 indices, I suppose, and then this again is some trace times some integral, and also again that there's a finite part which multiplies is a trace that is 0, and the divergent part which multiplies a trace that is 0, but you can regularize it dimensionally, and so in the end you also get a finite result. And in terms of what you expect is, again, you expect the coupling squared, because now you have 2 external vertices for gauge fields, and you expect a gauge invariant combination. This was with epsilon mu nu. This one will be with epsilon mu nu rho sigma. So what is the combination is actually epsilon mu nu rho sigma, f mu nu, f rho sigma, and then some 2's and pi's and i's and minus. Yeah, so in Minkowski space, this is what you get. The anomaly is proportional to e squared epsilon mu nu rho sigma, f mu nu, f rho sigma.
Professor,
Yeah.
that relation that you said that anomalies in 4 dimensions come from triangle diagrams and in 2 dimensions loop diagrams, where do you get that?
Well, okay, so I have to remember how that how that goes. Well, so this result. So we're expanding in. We're expanding in E, right? But the result, the final result, has 2 vertices, external vertices. So there's E squared. So in here, I've calculated the term that was proportional to E. I ignore the term proportional to E squared. What will happen in 4 dimensions is that this integral is 0. The whole thing is 0 once you calculate it, and then you have to go to E squared, and in E squared, the only thing that is non-zero, finite, is the loop integral, the one loop integral part, right, with 2 external fields. And so that's why I said it's much longer calculation. You have to calculate much more terms. And then the only one that is non-zero comes from this E squared, but with one integration. So you see, integral of y in here is over the external gauge field, so that's not a loop integral. But there's only one integration over momentum, right? So there's in E squared there would be an SF from X to Y, and then an SF from Y to Z, and then an SF from Z to X, right? So corresponding to, so X being the current, and Y and Z being the external gauge fields, right? And then when we go to momentum space, this becomes a one loop with 2 external gauge fields and 1 external current. And then again, what I said, you get the structure with a trace times an integral, and then you have to see that the integral has a divergent part and a finite part. The divergent part is 1/2 minus d, and the trace is also d minus 2 minus d. Sorry, 4 minus d now. So yeah, I mean, you know, it's just a longer calculation. You have to look at much more terms, and but the story is the same. There's nothing new happening. Okay. All right. So I think I'll show some. Yeah, I'll show something in the path integral that will be a little bit more clear why you get a triangle diagram. But yeah, I mean, in here you can just trust me that the E integral is, all of it is 0 in dimensional regularization, and the E squared part is only this triangle diagram is non-zero. All right. Now, let's go to properties of the anomaly. So there's a theorem called the Adler-Bardeen theorem that says that the anomaly is one loop only, and only comes from the given polygonal graphs. So here, I mean, in 2 dimensions, I just showed you that up to this order, we have the non-zero bubble anomaly. But I haven't said anything about what happens after at higher orders or at non-perturbatively. But this theorem tells you that that this is supposed to be true at all orders and non-perturbatively as well. Here I'll just give some plausibility arguments. Just, you know, to see that this could be, it's consistent to be like this, but not that it actually is like this. The actual theorem is a bit more complicated. Also, the anomaly sometimes is called Adler-Bell-Jaquev anomaly. So the same Adler appears in the definition of the anomaly in the theorem as well. So what is the plausibility argument? Well, in d equal to 2, the result was a trace of 4 gammas and a gamma 5. And that, in the end, we've calculated this was proportional to d minus 2 times epsilon mu nu. But then it was times a log divergent diagram with 2 massless fermions. So 2 massless fermions is 1 over k. So there was 1 over k, 1 over k, and the integral d2k, which is log divergent. And in dimensional regularization, that means 1 over d minus 2. So d minus 2 cancelled, and we'll get something proportional to epsilon mu nu. However, if we keep this idea, you can see that the cancellation, this possible cancellation, will not be true. So this that kind of cancellation between a trace and a trace coming from gamma matrices that is proportional to d minus 2 and d minus 2 epsilon mu nu, and a loop integral is not possible at higher loops, and also not possible at higher points. So higher loops means that I have I increase the number of integrations, right? So then the divergence will be a stronger divergence, right? So we cannot cancel this. The divergence from the trace, it's always proportional to d minus 2. So it's always this leading divergence. Sorry, 0. So it's d minus 2, not d minus 2 squared or anything else. But this, at higher loops, you'll have a higher divergence. So so this is 1 over epsilon, but at higher loops is 1 over epsilon to the L. Then also not at higher points. So if I keep the loop, but I put higher points, then I have more more propagators. So one integration, but more propagators. Well, that doesn't work out because then I have integral d to k over k to a power greater than 2. So that doesn't work out. Okay, this is a a plausibility argument. It is not supposed to be a theorem. The theorem is itself, it's, as I said, more complicated, but we see that this sounds right. So what I mean is, in principle, there could be cancellations and so on. So it could be, in principle, it could be something very fine-tuned that happens, but it doesn't. Now, in d equal to 4, we will have a trace with 6 gammas and a gamma 5, which will be proportional to d minus 4 epsilon mu rho sigma. And then also a log divergent diagram with 3 massless propagators. So it's a triangle, right? It's a triangle. So I have 3 massless propagators. So something 1 over k, 1 over k, 1 over k. And then integral d for k. But then this one, the momentum structure is actually k alpha over k squared, because we have k slash over k squared as a propagator. So the gammas go into the trace, and we're left with k with an index. So it's actually k alpha over k squared, k beta over k squared, and k gamma over k squared. So I have 3 indices. So by Lorentz invariance, I can contract 2, but I'm left with 1, and that 1. So they're also not k squared. They're k plus combination of external momenta. So this will be, so with 3 indices, then I can contract 2 indices to have delta alpha beta, but then I'm still left with 1 that cannot be, it's a free one that has to be proportional to one of the external momenta. And so then dimensionally I have d4k, but divided by k to the 4, because I have 1 over k from the 2 propagators that were contracted. And then the other one, I peel off the numerator, but I'm left with the denominator, which is k squared. So it is d4k over k4. So this is a log divergence, which in dimensional regularization is 1 over d minus 4. So again, I have the same cancellation with d minus 4 from the trace and 1 over d minus 4 from the triangle Feynman diagram. And then this epsilon mu rho sigma. And then again, by gauging variance, this is supposed to be contracted f mu f rho sigma. And again, at higher loops, this cannot happen anymore for the same argument that this trace is proportional to d minus 4, or epsilon, whereas at higher loops, the leading divergence is 1 over epsilon to the L. So I cannot have, I still have something divergent. And then at higher points, as I said, I have more propagators. So I can, so the denominator has a higher power. So again, I don't have, so now it's a finite integral. And it was important that we had massless fermions, because if you have massless fermions, and massive fermions, I mean, here we considered the chiral symmetry, and for this particular chiral symmetry, you know, the mass term was not even allowed by the symmetry. But imagine that there is a mass term allowed by some symmetry like that, but they nevertheless do not contribute to the anomaly. You can try to give, you can try to figure out a similar argument about what kind of integrals could you have, and you can prove precisely that rigorously that massive fermions do not contribute. Another point is that this anomaly cannot be removed by a local counterterm, so it is a genuine quantum anomaly, a genuine effect of quantum mechanics. What we can do in 4 dimensions, so I'll describe what happens in 4 dimensions, because, you know, this is the thing that's of most importance to physics. The d = 2 example was just because it was easier to calculate. I should have done the 4-dimensional one, but it's just longer, so I just thought it wasn't worth it doing so much algebra. And so in 4 dimensions, what you can do is you can figure out that f mu, f tilde mu, which is epsilon mu rho sigma f rho sigma over 2. So this combination is 4 times, is a total derivative, is 4 times del mu of epsilon mu rho sigma a nu d rho a sigma. Since it's a total derivative, I can subtract it from the current. So remember the I'll never be able to write this. Sorry. Anyway, this so the anomaly was d mu j mu vev is equal to some number times this f mu nu f tilde mu nu. So so now then I can rewrite this as vev of d mu of j mu minus these numbers times epsilon mu rho sigma a nu rho sigma a nu d rho a sigma, right? So in other words, I can redefine the current to be j tilde mu 5 is j mu 5 minus e squared over 4 pi squared epsilon mu rho sigma a nu a rho a sigma. And then this is conservative in the sense that now the relation is del mu j mu tilde 5 vev is equal to 0. The conserved charge is then integral of a space of j0 5 tilde. So this redefined current is conserved, but it's not gauge invariant, because if I vary the gauge field, the variation of a mu is d mu alpha. J mu 5 is gauge invariant because, well, yeah, it's psi bar with psi, so the exponents cancel. But this part is not gauge invariant. So if I vary this one, if I put here d mu alpha, this part is 0 because I have d rho with d mu, but with anti-symmetrizing rho and mu. However, the contribution when I vary this a mu is not 0 because now I replace it d mu alpha. So the variation of the current g mu 5 tilde is this thing times d mu alpha times d rho a sigma. Okay, so this sounds like a trick, and it is in a sense kind of a trick, because, well, what does it mean to have a conserved current that is not gauge invariant? But the interesting thing is that now the charge itself, the charge coming from this current, is invariant. So the charge is the integral of J0 of J tilde 0, 5 over space. So then this is the charge, the unredefined charge, the integral over space of J0, 5, minus what I'll call a Chern-Simons term or Chern-Simons action that depends only on AIs with I spatial index. So there's this E squared over 4 pi squared. There's the integral over space that we have. And then the index mu equal to 0 comes on epsilon. But epsilon mu rho sigma is the same as saying that I put nu rho sigma to just spatial indices, but still totally anti-symmetrized. So epsilon ijk, and then times ai the dj ak. Okay. So the redefined charge is the original charge minus the Chern-Simons term, but it's invariant because actually this this variation of the current is a total derivative. So this del j mu 5 tilde is a total derivative because I can pull off d nu and pull it here. Indeed, if d nu is here and if I act on A, well, that's is symmetrized d nu d rho, but times anti-symmetrized d nu d rho. So that contribution is 0. So the only way it acts is in here on alpha. So this term is actually a total derivative, which means when I integrate it over space and I put mu equal to 0, yeah, I get a contribution that is 0, because by definition, variation of the gauge field is 0 at infinity. Okay. So I get a boundary term, but the boundary term is 0 because alpha is equal to 0 at infinity. So, all right. So the redefined gauge field, redefined charge of the symmetry is makes sense because it's conserved and it's gauge invariant. So All right, now let's move on to the non-abelian case. In the non-abelian case, we have we can embed this chiral symmetry in the non-abelian theory of massless fermions. So the Euclidean action for the massless fermions, again, psi bar gamma mu d mu psi, but d mu now is non-abelian, has del mu plus g a mu a times the symmetry generated as TA. So, you know, I can embed the U1 chiral symmetry into this theory. So psi going to e to the I alpha gamma 5, psi is still a symmetry of this action. And then, not surprisingly, if I calculate this thing, so the argument is still the same, that d mu g mu 5 should be proportional to g squared and epsilon mu nu f mu nu f rho sigma. But now there's an issue because this is non-abelian, so it's only proportional to, only possibility is be proportional with a trace of this thing. So this is what the result is. It's just the trace of this result. Well, with some, yeah, trace of this result, which is trace of the non-abelian version of this result. So because of that, this anomaly, it's called sometimes also the current anomaly, but sometimes the singlet anomaly. Singlet in the sense that it's the trace of this f mu nu f tilde mu nu. Now we can note that the this trace of f mu nu f tilde mu nu can be rewritten as epsilon mu nu rho sigma. It's a total derivative, like in this case, in the abelian case. In the abelian case, I wrote it like this. Now I also have a term with proportional to a cubed. So is d mu for epsilon mu nu rho sigma trace a d rho a sigma, which was what we got in the abelian case. But then now it's plus 2/3 a nu a rho a sigma. So because of that, now I repeat the same argument, and I have that there's a redefined current j mu tilde 5, which is j mu 5 minus g squared of 4 pi squared epsilon mu nu rho sigma times this trace ADA plus 2/3 AAA. And I also redefine the charge. Q5 tilde is Q5 minus the Chern-Simons action, which is now g squared over 4 pi squared integral over space epsilon ijk trace what we had before ai dj ak, but then now plus this 2/3 ai aj ak. Now, unlike the abelian case, under a gauge transformation, the gauge transformation in the non-abelian case is that AI goes to the gauge, the parameter matrix U times AI times U minus 1 plus 1 over G di U U minus 1. So under this gauge transformation, the Chern-Simons transforms by 2 pi times an integer. So more precisely, so if you plug this in, do the algebra, the Chern-Simons Chern-Simons action goes to Chern-Simons action plus 1/4 pi squared times the integral over space epsilon ijk times trace of this diu u minus 1, dju u minus 1, dku u minus 1. But this extra term is a topological quantity that depends on the topology of u, topology of this gauge transformation, called the winding number n. So what that means is now the Chern-Simons term is not invariant anymore under these so-called large gauge transformations, which have non-trivial winding number different than 0. So what means that these gauge transformations sort of wind non-trivially around the space at infinity. So they are why they are large, because they wind. That means that they're not smoothly connected with the identity. You cannot deform the parameters in U smoothly so that to go from U to 1. Well, that in turn means that Q5 tilde now it's not gauge invariant anymore. So the global symmetry is explicitly broken by this anomaly. So in this non-abelian case, the anomaly breaks the symmetry to well, usually to a discrete subgroup. The term that appears in this anomaly, this epsilon mu nu rho sigma trace ADA, this trace F mu nu F tilde mu nu, is called the is also a topological quantity. So this winding number is a three-dimensional topological quantity in 3 Euclidean dimensions, in spatial dimensions, I, j, k. But this trace F mu nu F tilde mu nu is a 4-dimensional topological quantity called the Pontryagin index, or the instanton number. Okay. So up to now, we have discussed the anomalies in global symmetries, which are good anomalies in the sense that they have physical implications. You can measure what the anomaly is in some sense. Yeah, so they have applications. You will see that it means like the pion can decay in a certain way given by this anomaly. However, there's a different type of anomaly which appears in gauge symmetries, in local symmetries. So those are bad anomalies. They signal a breakdown of the quantum theory. The quantum theory is inconsistent. So you cannot have such a theory. Such a theory is inconsistent. You cannot have such theory in nature. That means in order to have a good theory, you have to cancel these kind of anomalies. So you must have contributions from different fields that cancel this local or gauge anomaly. This gauge anomaly appears if you have chiral fermions. Chiral fermions means in 4 dimensions field psi that are projected onto the left or right parts. That is, with this projector, 1 plus minus gamma 5 over 2. So these chiral fields, if they're coupled to gauge fields, will induce a potential anomaly. So that means the Euclidean action that we're interested in is psi bar. So I would say this last psi, but if you remember, we said that for chiral fields, I can just put this for free, this 1 plus gamma 5 over 2. Well, because the projector squared is equal to the projector itself. So this projector acting on the left, for instance, will imply the that I can use it or replace it with one projector only itself. That means with psi itself, psi left itself. So if I have this action, which is an action for left chiral fermions, then we have another current for the gauge symmetry, for the local symmetry, which is what? So, I mean, calling this a gauge symmetry, remember, is confusing. What we mean by we discussed this when we talk about the Noether currents. So it means that we don't have del mu j mu equal to 0 conservation. When we say Noether current, we mean something that's covariantly conserved. D mu j mu a is equal to 0. But nevertheless, the formula for this Noether current is the same. It's the variation with respect to del mu psi, which means I remove this term, so I just psi bar 1 plus gamma 5 over 2. And then I still have the gamma mu from this slash in here. And then I replace the d mu. Instead of the d mu psi, I have Ta, the generator of the symmetry, times psi. Now, similarly to the global case, as I said, we have a potential anomaly. And can also come from the Jacobian of the transformation of the measure, or otherwise from the triangle graph. And then by the same kind of calculation, we'll find that we have at one vertex not del mu j mu a, but d mu j mu a at one vertex, and then at the other two vertices a nu and a rho. Well, one can do the calculation and find that what we obtain is the following. Well, in here we have the TA. In the current we have the TA. So inside the trace, so we had this trace appearing in the singlet anomaly. We had trace f mu nu, f tilde mu nu, which was written as a del mu of a trace with a dA plus 2/3 a. But now we have the anomaly is equal to del mu, this number, epsilon mu nu rho sigma, trace, now TA, because I said we have the this insertion of TA, and then ADA, but then the coefficient in here is different. It's not, will not be 2/3, but is one half, A nu, A rho, A sigma. We'll explain a little bit later why the coefficient is different in the next lecture. We also observe that, so since I have this TA, and then these A's, they also come with TA. So this A nu is means A nu B TB, and A sigma means A sigma C TC. So the we see that the anomaly is proportional to this DABC, which is trace TA TB TC. But if you look in here, this is symmetrized with respect to the TB TC, because it's symmetrized because it's antisymmetric in nu and in A nu and A sigma, and then you also have to take wait, why do I see that? No, sorry, nu and sigma. Yeah, sorry. Yeah, it's antisymmetric. So it's antisymmetric in A nu and A sigma. But then if I change A nu with A sigma, I have to also partially integrate d nu, d rho onto A nu now to have the same, to get the same ADA term. So I get an extra minus. So I get two minuses, one from antisymmetry in nu and sigma, and one from partial integration. And then it means that in the end it's symmetric in the indices B and C. So I get this combination, DABC, like this. And then this this time with four generators is actually 0, I think. Or it doesn't contribute in some way. So yeah, it doesn't contribute to the final anomaly. If you calculate it, it will be 0. So so what is the meaning then of the gauge anomaly? Well, so the gauge anomaly means we will obtain a term that is proportional to DABC, but there's contributions coming from. So I wrote this triangle anomaly with external gauge fields here, and then the current. But in the loop in here, I had one type of massless fermion. And in principle, I can have several types of massless fermions. And I can and in order to have a consistent theory, I have to have to cancel the contributions from the various fields. So so this will be what will happen in the standard model. We'll see that we will add up representations of fields such that when we sum over the things that run in this loop, we get total anomaly being 0. So d mu g mu a is actually 0. It has several contributions of this form, but all of them cancel. Again, the sum of all of them is 0. And the final point, I haven't explained to you why this is a bad anomaly. Why do we need to cancel this one if we kept the anomaly for the global symmetry? Well, the answer is very simple. The gauge symmetry is a local symmetry, which is something like d mu of an alpha. So with this d mu of an alpha, I can put to zero some degree of freedom. So the gauge symmetry removes from the theory a degree of freedom. But if we would have an anomaly, that would mean we would not have the local symmetry at the quantum level anymore. So at the quantum level, we would have the number of degrees of freedom before we removed the 1. So we would have different numbers of degrees of freedom in the classical theory and in the quantum theory. That's clearly a nonsense. So that cannot happen. And this is why we need to cancel the this gauge or local anomaly. All right, so that's everything I wanted to tell you today. Next lecture will continue with the analysis in the path integral, and after that with physical applications of the anomaly. Yeah, so that's everything. Do you have any questions?
I have a question about the exercise of the last lecture.
All right.
That
Let me look at it. Oh, wait, what was it?
yeah, I think it's this, yeah. So so can you go down a little bit, just a little quick. So what's the difference? I don't understand these state vectors. What's the difference if a state vector with an epsilon and without an epsilon?
Well, the point is that they're all they all depend on epsilon, right? So all the variables depend on epsilon. So so what we're doing is we're expanding we're expanding the field, the yeah, we're expanding the field in terms of a basis, but the coefficients themselves depend on epsilon. So then also the basis must depend on epsilon, since we're right. I mean,
But
that's one way of thinking about it.
but in some cases, it depends on epsilon. In some others, you wrote if without an epsilon.
I'm sorry.
So, for example, in some cases, you wrote it with an epsilon, and others there's no epsilon.
Well, yeah,
Like
yeah. So
one,
yeah. So that's another point. So you can define this thing without an epsilon as a finite tree level. So this is a tree level thing, right? A0 is at tree level, right? So it's a finite thing. So there's no need to introduce an epsilon, right? You can at tree level A0 is independent of epsilon, but then at the one loop level, in general, things are not finite, right? They're divergent. So so we need to have epsilon dependence. That's why I wrote like this. A0 is independent of epsilon just because it's tree level and there's no divergence. But the other ones are epsilon dependent in general. Amplitudes are in general are at loop level are epsilon dependent, right?
okay.
All right. Any other questions? Well, if not, I will see you on Thursday at 9. Yeah, that's it. Bye.